We now have an extremely interesting part of the program, where you as an audience are playing a key role, since the interaction with you all will be decisive. And for that I would like to ask Roger Jaspers from the Eindhoven University to further explain this session and to introduce all the speakers involved. Roger Jaspers.
Yes, hello. Now it's your turn. We are in this prize session now. 2 prizes have been awarded. One for the teacher, because it's very important that we teach, that we inspire the new people. Also, the communication is important. For that, you had the prize for the best paper in NTVN. I think next in that line in communication is presentation. How often do we sit in a room like this and listen to a presentation? Sometimes we're very happy. It's inspiring, motivating, giving us, yes, it's physics. But also sometimes I feel, okay, well, it could be better. So not today, for sure. Today we only invited good speakers. 3 of those are listed here already. So to stimulate people to put effort in good presentation, we have this prize. Prizes, or this contest, is for PhD students and young scientists, where we want that they demonstrate that you can keep the attention for the public, for a broad audience. Show how nice your work is. Give that message, the real message of that, to the audience. So we ask you to judge these 3 presentations on these points. The prize, the award, was open for all PhDs and young scientists. We received 25 applicants. Then I sat together with 2 of my colleagues, Richard Engelen, the one you know, he just stand here 2 minutes before me, and Hjalmar Mulders. Based on the abstract, we invited 8 people to give a pre-presentation to this committee, and we selected those 3 here. Now the task is yours. We have 2 times Nick, 1 Ivo. We have 2 Dutch, and it's international, so we even have a Belgian one. We go from crime scene investigations, we go to weather forecast, just to the holy grail of metallic hydrogen. Everything is in there for making this a wonderful session. So I would like to invite Nick Laan as the first speaker. Give him a big hand, and then... You ready for it?
Yes, yes I am.
The floor is yours for the next 12 minutes. I will
Thank
warn
you.
you 1 minute before.
Yes. So as a PhD student at the University of Amsterdam, I'm with a soft matter group where we investigate all kinds of soft matter. And in my case, I investigate blood. And this presentation is going to be about why and how. So when a crime scene investigator comes to a crime scene, he wants to determine what has happened and where it has happened, amongst others. And you can do this by means of bloodstain pattern analysis. And one of these bloodstains, specifically the one I'm interested in, is the impact pattern. An impact pattern is created when an object, for example a hammer, strikes a volume of liquid blood. For example, a head. Heads are filled with blood. And accordingly, droplets disperse through the air, and when they hit a wall, they'll form patterns like these. And specifically from these kinds of patterns, we can determine where the blood came from. And for that, I've got a little example for you. This is Bob. Bob gets hit by a hammer, blood flies everywhere, but Bob disappears. And we want to know where was Bob when this happened, so we can reconstruct the crime. So first we're going to look at the individual blood droplets and the directionality, which way were they going, and do we have a common point where they could have come from? If so, we say, okay, this can be an impact pattern. Next we're going to choose any number of stains. We're going to look a little bit up close. Because we want to determine the impact the droplet hit the wall with, the so-called impact angle. Well, we can determine this by just taking the arc sine of the width divided by the length of the elliptical shape of such a stain. Well, we do this for a lot of stains, and next we can draw a string, a line, away from these stains under this angle, and where they come together we say, okay, this is where the real blood came from. Well, this can be done with real strings, which is actually done still today on the crime scene, but of course we can also just do it with computer programs. Well, what we see here is that all these straight lines represent the flight trajectory of the droplets. But we all know droplets don't fly in straight lines. They're curved because of, mainly due to gravity. So when you're going to string a line back to where it came from, you're actually overestimating the height of your source. And it's already been measured that if you're just 1 meter away from the wall, 1 meter from where your pattern is, you can already have a height overestimation of 45 centimeters. So what can you actually say about the position your victim was in? What can you actually say what has happened on the crime scene? So I want to solve this. And to do that, I want to determine this curve trajectory by taking gravity into account. And for that, I need 4 parameters. First parameter is the position of the stain. Well, we can determine that very easily, just measure it. Second parameter, the impact angle. I just showed you, take the width and the length. Third parameter, the volume of the droplet. For this, we can do it just by a 3D scan of our stain and calculate back what the original volume was from a dried stain. But then fourth, the impact velocity. How are we going to determine that? So is it possible to determine the impact velocity by means of the size, the volume of a blood stain? So the principle is quite easy. If you have a low impact velocity, you'll get small, thick droplets, and if you have a high impact velocity, you get big, flat-out pancake-like stains. And this is what I've been investigating to determine a relation between the size of our stain, Dmax, the volume of our original droplet, D0, and the impact velocity. And to do so, we use the Weber and Reynolds number. Here, the Weber number is the ratio between the inertial forces, the forces which make a droplet spread, and the surface tension, which want to keep the droplet together. The Reynolds number is the ratio between the inertial forces and the viscous forces, which slow the droplet down in spreading. Well, accordingly, we can define 2 different kinds of regimes. The first regime is the capillary regime. Let's say viscous forces don't matter, we don't have those right now. If we use energy conservation, we can deduce that Dmax over D0, our spreading ratio, should scale with the Weber number to the power of 1/2. On the other hand, if we say for the viscous regime, we say, okay, surface tension doesn't matter. In that case, Dmax over D0 should scale with a Reynolds number to the power of 1/5. Well, we've already seen that for droplets, for water or blood, actually none of the 2 models actually come back in our data. Because droplets, the spreading depends on both the viscosity and the surface tension. So we thought, okay, what if it's a transition from one regime to the other, and almost all the droplets we measure are in between? Well, therefore we adopted an approach of Eggers et al. And we could say that, what if Dmax over D0 times the Reynolds number to the power of -1/5 should then be a function of what we call the impact number, Weber times Reynolds to the power of -2/5. Well, to investigate, we of course had to deposit droplets. Here you see a blood droplet fall, and as it hits the surface, it spreads out. You see a rim form, it slows down. Finally, it reaches the maximum diameter, and then it sticks to the surface. It doesn't contract anymore, which is very useful for us. So we did these kinds of experiments. We did them from all kinds of different heights. And of course, we didn't only do it for blood. We also did it for water, and for water, glycerol mixture, so we could get a large range of Weber and Reynolds numbers. And these are those results. So I've plotted Dmax over D0 times the Reynolds number to the power of -1/5 for our impact number. And we can see that all our data points overlap. They're all collapsing upon one another. So right now I can say, okay, this is how droplets spread. This is how they behave. But I don't have a quantitative relationship yet. Well, for that, we used a mathematical approach, the Padé approximant, which says we can interpolate between two different kinds of power laws, the Weber to the power half and Reynolds to the power of minus 1/5. And you can see that with just one free parameter, which turned out to be 1.24 fitting parameter, we can fit very nicely to all this data. So we have an equation which predicts the impact velocity. However, all those data were for droplets falling straight down, while on the crime scene the droplets hit the walls on an angle. So we need to take this impact angle into account. Well, it's very easy. So instead of taking the diameter of our stain, we only use the width. And we say, okay, the width spreads as if it would for straight down, so we also have to take the velocity perpendicular to the surface. And we rewrite our equation like this, and now we can actually determine the impact velocity. So we did. So here you see the calculated impact velocity as a function of the measured velocity. And it's very clear, there's very high correlation, we can determine the impact velocity very accurately. But of course, this is based on all our data points we already had. So we just repeated these experiments for blood on all kinds of different surfaces: glass, stainless steel, acrylic glass, Trespa, POM. POM is a standard white plastic, and also under a lot of different kinds of angles. And once more we see, okay, there's a very high correlation. We actually can determine this impact velocity. So yes, we can do it. Of course, probably you're curious right now, so if you have that impact velocity, can you actually determine the curved line and where blood droplets really came from? Well, to investigate this, we went to the Netherlands Forensic Institute. They have these very nice cubicles over there. And in these cubicles, we can play around with blood. So they have a hammer on a spring. We put a little bit of blood down, we pull the hammer back, and bam, and we have an impact pattern. We let it dry, and next we let actual blood stain experts choose any number of stains they would normally, and then we started measuring. We started measuring where they actually came from. So I got one example for you. We knew where the actual origin was: 1 meter from the wall, 1.5 meters from the sidewall, and a height of 1.44 meters, and with 31 stains. And if we would do the straight line approximation, this is what we would get. So you see here, X and Y are determined pretty accurately, only the height was determined 30 centimeters too high. Even if we take the uncertainty into account, the actual origin would not fall within it. Now, if we would determine the impact velocity for every single stain and take gravity into account, this is what we would get. And now you can see we're only 3 centimeters below the actual origin. Never before was it possible to determine the origin this accurately. And in this case, it would already mean the difference between a sitting and standing person. So to conclude, I've showed you what the actual spreading behavior of droplets in general is, and that we can determine the impact velocity from dried blood stains. And we apply our fluid dynamical approach to real blood stain patterns and can determine way better where the origin was than the current methods in use. And this, I think, is a very big step forward in forensic science. Thank you for your attention.
Thank you, Nick. They applauded for you, so apparently it was well done. We decided in view of this scheme to allow no questions, or it should be a very urgent one. There's no one daring to become suspect in these conditions. So now we go to a completely different topic. The weather forecast or clarity of ground frost. It's from Ivo van Hooijdonk, from Eindhoven itself here. He's preparing now to get his electronics ready so that you can see him and hear him. And there he comes from behind the curtain. Give him a big applause. It's Ivo van Hooijdonk.
Ja, hij staat op de ding. daar. En heb je hem opgezet al naar beneden. En dan staat hij klaar.
Nee,
Of had hij hem nog niet gedaan?
hij staat nog niet klaar.
Some technical issues.
Oh, it's there.
Okay, good afternoon. Welcome. April last year, this news article, which should appear, appeared about fruit farmers here in the Netherlands. And the night before had a very clear sky. Now, as we all know, nights without a blanket of clouds can become quite cold. We've seen it this whole week, this very morning. And especially around April, there's a good chance that ground frost will occur. Now, of course, for these farmers, it is very important to have an accurate prediction of whether or not ground frost occurs. So they might decide to take measures against it, just as here in the article. However, weather models are not very good at predicting situations where ground frost occurs. Here we see the typical overestimation of the surface temperature by weather models for the Northern Hemisphere. And for example, for Europe, we can see that this can be up to 4 or 5 degrees. And the reason for this error is a lack of understanding of the fundamental processes. So the models have to rely on ad hoc parameterizations rather than physics to make a prediction. So clearly something is wrong. But what exactly is the process that I'm trying to understand? We observe, and this has been known for many years, that when the sky is clear, so there are no clouds, the wind is a decisive parameter for the dynamics during the night. Strong winds generally lead to relatively warm surfaces and strong turbulent motions in the lower atmosphere, while weak winds tend to have much lower temperatures and almost laminar-like flows. But this is based on experience, not on understanding. And interestingly, we also see that in addition to the temperature effect, there is a difference in airflow characteristics. And this is one of the reasons Gerard van Rooij will talk about energy storage this afternoon, as wind farm output becomes highly variable and unpredictable in these kind of situations. But the difference in characteristics also touch upon a fundamental issue in physics. And that is the prediction of the transition from turbulent flows to laminar flows. The other way around, we can often use linear perturbation theory. So meaning we take a laminar solution, give it a little kick, and see if this perturbation grows in time. And if it does, it becomes turbulent. But we cannot use this for turbulent flows, as we do not have a solution. There is no solution to give a perturbation to. But if we can understand the issue of ground frost, at least we have one example where we can tell something about such a transition. So let's start with the everyday physics of ground frost. During the day, the sun heats the surface of the earth, and the surface in turn heats the air from below. So we get warm rising air and cold air coming down, creating a circulation. And with the added effect of the wind, everything becomes well mixed. So temperature and momentum are evenly distributed throughout the, let's say, bottom kilometer of the air. But at night, this changes. After sunset, the surface emits radiation and thereby loses energy, so it becomes colder and cools the air from below. So we get cold, dense air near the surface and warm, lighter air aloft. So there's a density gradient. And this results in a competition between the wind trying to lift this heavy air, to mix the air, and the density gradient fighting against this vertical transport, trying to unmix the air. And we can understand this a little better if we look at the surface energy budget. Now, this all takes place in the so-called stable boundary layer, which is, let's say, the bottom 50 to 100 meters of the air at night. And here on the right, you see the surface energy budget, or surface temperature, if you like. And it depends on two main actors. Qn, the radiation emitted by the surface, which is a loss term for the energy equation. And we see H, and H is a supply of energy. It is the turbulent heat flux, which accounts for the amount of warm air transported down to the surface by turbulent airflows. So by the wind. And we can go somewhat deeper into these two energy fluxes. The radiation is relatively easy, as under reasonable approximation for clear skies, we can consider it constant, represented by the horizontal dashed line in this figure. But the turbulent heat flux is more complicated, here shown by the blue curve, as it depends on the temperature gradient itself. Here on the left, for neutral conditions, it disappears because in that case there are no gradients, so no transport can take place. But also here on the far right, for strongly stratified conditions, so when the density gradient is very strong, it disappears, because then the density gradient prevents any vertical exchange of energy. So that means that somewhere in the middle, we must have a maximum. And the height of this maximum strongly depends on the wind speed. This sketch could represent a night where the wind is relatively strong. And in that case, the maximum lies above the QN line, and we can reach an equilibrium. Here, around this point, where energy supply and energy loss are in balance. And dynamically, we can see this as follows. We start off in neutral conditions around sunset, and as the surface cools, the gradient increases, and we follow the blue curve, until at some point in this region, the energy supply becomes larger than the energy loss. So the gradient decreases again. So through negative feedback, and that's important, negative feedback, we end up in this stable equilibrium. But what now if the wind is weaker? In that case, even the maximum possible energy supply is not enough to compensate this energy loss by radiation. So that means that the loss of energy is always greater than the supply, and the temperature gradient keeps on increasing. So at some point, the energy deficit may be represented by this arrow, but sometime later, it can be this or this arrow. So it gets worse. So we see a positive feedback. And that means a bifurcation occurred, a sudden change in dynamical behavior from positive or from negative feedback dynamics to positive feedback dynamics. Now, the precise temporal behavior in this region is still under investigation, but fact is that ultimately this leads to very strong gradients and very low temperatures near the surface. So we see indeed why, for weak winds, the likelihood of ground frost increases. But this picture reveals another interesting aspect, and that is that the surface energy budget defines a velocity scale. And it is that wind velocity for which the maximum in the heat flux exactly balances the energy loss by radiation. Here, the black curve. And we can find an analytical expression for this wind speed. Here shown at the bottom. Now, without worrying about the details, important is there are some assumptions and approximations involved. But due to this 1/3 power over here, the result is very robust to the details of these approximations. At least in theory. So we need to check with some observations if things are really work this way. Now, for that purpose, I analyzed observations from the Cabal Weather Tower here in the Netherlands. It's operated by the KNMI, the Dutch Weather Service. And I looked at over 4,000 nights in ensemble averages as to reduce the scatter that's of course abundant in the atmosphere. That means that in the following results, each data point contains data from over 100 nights each. And let's look at some of these results. Now here we see the temperature difference on the vertical axis between the surface and some reference altitude, in this case 20 meters. So the higher this value gets, the lower the surface temperature is. And we see it as a function of the wind speed at the same 20 meters. But the wind speed is normalized with the theoretical minimum wind speed I showed you 2 slides ago. Now the color of the dots represent the regime. So blue for the regime with strong winds where we can reach an equilibrium. And red for the regime with much stronger gradients, let's say where there's danger of ground frost. Now I'll also show you 2 snapshots of numerical simulations, just to give you a feel of the difference between the laminar and the turbulent flows. So laminar and turbulent. And let's add some more data to this figure. Here we see basically the same data for 10 meters, 40 meters, and 80 meters as well. And we see the same pattern emerging. The red regime systematically has larger temperature differences than the blue regime. And we also see that the transition between the 2 regimes falls into the same value of this normalized wind speed, this normalized parameter. And that's an important result, because we can compare it with a parameter that's currently being used in operational weather models. And that's the one we see here on the right. Now, without going into the details of this parameter, we see that it works quite well in both limits, so on the left and on the right. But in the middle, there's this large gray zone where we cannot uniquely relate this parameter to a particular regime. And in that sense, our new parameter outperforms this operational and also textbook parameter. But why does this work? What do we do that suddenly a transition becomes predictable? And the reason is that we make the prediction for an approximated field, so for a surrogate of real turbulence. But due to the bifurcation, the sudden change in behavior, and the strong dependence on the wind speed, we still predict the correct behavior. So in summary, I introduced a theory that seemed to predict this transition between regimes and bifurcation quite well. And this is also confirmed by observations. So when we put this all together, we can say we understand how ground frost forms and the mechanisms behind it, and we can quantify its prediction. Now, we've also seen that there's still some work to be done on the temporal behavior especially, and maybe I can tell you something about that next time. For now, I'd like to thank you all for your attention.
Thank you, Nick. Ivo. I'm not sure what is allowed if you win this prize to come a second time to compete for that, but I will read the rules for that. He already left, so I'm not going to ask for any questions because then he has to come back. Brings us to the international guest here. It's Nick van den Broek, University of Antwerp, and he's going to tell you about metallic hydrogen. Are you behind me? Okay. Please prepare everything. You ready for it?
Yes, I
you
think...
have 12 minutes to convince us whether you or any of the others is the best speaker.
Okay,
So please, success.
Okay, so thank you very much. Hello everyone, my name is Nick van den Broek from the University of Antwerp. And today I want to tell you something about how nano-optics can shine light on the quest for metallic hydrogen. Now, hydrogen is something that you all know. It's, well, the first element in the Mendeleev's table. It's one of the simplest atoms we know. It's been discovered 400 years ago, but it seems that it still has some secrets to reveal. 80 years ago, two theorists predicted that hydrogen, which usually is found in its molecular form, if you compress it under very high pressures and very high temperatures, you can get it into an atomic form. Now, this is an interesting form, because this atomic state, if you do this, then the band gap will close, and thus meaning that this atomic hydrogen will effectively become a metal. And this is very interesting and important to know. For one reason, in astrophysics, if this is true, if we ever find this metallic hydrogen, then it is predicted that very large bodies in our stellar galaxy should have this metallic hydrogen in its core. For example, as indicated by the huge magenta region in this image of Jupiter. But it also has technical applications. For example, it should be metastable, which means that once we form it under high pressures and high temperatures, we can get it back to ambient temperatures and pressures, and it should still retain its metallic form, which is interesting because it's predicted to be superconducting up to 290 kelvins, which would make it one of the first real candidates for room temperature superconducting. But it doesn't stop there. If we make this and can get it back to room temperature, then we can also use this in rocketry, and it would revolutionize rocketry because due to the high dissociation energy, when it goes from its from its atomic form back to its molecular form, outperforming our regular fuels we have now tenfold. And this would mean that we can effectively create single-stage rockets to get into space instead of the triple-stage rockets we need now. Now, this is all fine and dandy, but we haven't found this metallic hydrogen yet. And a very large part of physics, namely the high-pressure physicists, are very hard looking for it to find this metallic stage. Among those is Professor Silvera, which is a collaborator of mine, and he and his experimental research team, they are looking for this using something called a diamond anvil cell. Now, a diamond anvil cell exists out of two diamonds put together, tip to tip, and then if you press them together, you can create pressures up to about 300, 350 gigapascals, which is something that you find in the center of the Earth. Inside, between these tips, you put the hydrogen, which you want to, which is the experiment you want to run, and around it you put a rhenium gasket just to keep things contained. Now, the reason we use diamonds for this is firstly because it's the hardest material we know. It can cope with these high pressures, but also because it's optically transparent, which means that we can send light straight to the experiment and see what's going on inside our cell. Now, if we zoom in closer to the cell, then we still have the diamonds, we have the hydrogen, and we have additional layers, for example, a tungsten absorber. The function of this absorber is that if we send in a nanosecond laser pulse, this absorber will capture that heat and release it again, capture that energy and release it again as heat into the environment, effectively turning the hydrogen into the metallic hydrogen we are looking for. Then we can send in a second laser and measure the reflection and transmission and see what we have found. Now, at this point, myself and my promoter came into the discussion and we said, this is nice, but we don't think this is what's going to happen. We think that instead of a very nice, well-defined slab of metallic hydrogen, you're going to get some kind of gradient, which is logic because the transformation from molecular to atomic to this metallic hydrogen follows the temperature. It's temperature activated. And as we all know, if you have a heat source on one side and a heat sink on the other side, we have more or less the exponential decay of temperature. And if you combine this temperature profile together with the Arrhenius formula, which comes from chemistry and which governs the reaction rates between two sides of a reaction, then you can get this kind of profile that we expect for the metallic hydrogen. Now, this would be very interesting for nanophotonics. So coming from space, we're going back to 10 nanometers, because these layers are usually 10 nanometers. In nanophotonics, we're trying to improve the description of how light interacts with matter, and one of the things we're trying to implement now, which we think is the next step, is something called the electronic spill-out, which happens that electrons in metals, at the edge of your lattice, the electron doesn't stop. They go out of it, and you get a smoothing electron density. And this is just a really exaggerated version of that same effect, more or less. So this could be interesting for us as well. Now, our collaborators did these experiments, and here is what they found. The first line you should look for is the black dot here, which shows you the laser power compared to the temperature achieved inside the cell. And you expect this to be more or less linear, except here in the green window, they find some kind of a plateau, which means that even though you put in more energy, the temperature doesn't rise, which is usually a nice fingerprint of some kind of transition going on. So that's a good thing. Also, when this plateau starts, you can see that the reflection, which is the blue line, suddenly rises and the transmission drops, which is also what you expect if a shiny metal is starting to form. So these are good indications, but if you want to really prove to the community that you found this metallic hydrogen, you need to support this with theory. So that's where we come in. We tried to model this diamond anvil cell and see what's going on inside. And we did this, of course, by starting with the Maxwell equations, because we want to know the optical properties of what's going on. And we combined this with a model for the metal. Now, the thing that we did differently compared to everyone else is that we included here this profile function, which allows us to include this density. Now, this is difficult because at this point you can no longer solve these differential equations analytically, so you have to go to numerics. But what we can do is, if we combine this and use the symmetries we have in our diamond anvil cell, then we get one single equation we still have to solve in the computer. We can discretize this, and what we do now is we discretize on the grid. On one hand, we have the incoming wave. This is the laser we sent in, so we know this one. Secondly, we have a reflected wave. This is something we don't know, which we're trying to calculate, so we just take a guess at it. But if we guess it, then we know what's going on this side, and we can use the formula I showed you on the other slide to hop to our entire system and find the transmission on the other side. Now, for just a random guess of this reflected wave, to be mathematically correct, there's going to be an unwanted incoming wave from the other side as well. Otherwise, the maths don't fit. So now it seems quite straightforward that what we're going to do is we're going to try to get rid of this unwanted wave by taking better guesses. Now, of course, we're not just going to randomly guess at this. You can rewrite this into a nice minimalization problem, and your computer can solve this in somewhat of a minute or something. So it's really fast. Using this model, we calculated what would happen for the metallic hydrogen. So here you can see that profile that I showed you, and then here in blue again is the reflection. The solid line is what you would get if you get a well-defined slab, like everyone in high pressure community is using right now. And the dots is what we get with our profile. And here you can see that there's a big change in the reflection, up to 30% lower reflection. And that's a quite significant thing if you're looking for proof that you found something and it's 30% off. So you can see that in the beginning it's quite okay, that's the metallic region just happening there, but then the profile becomes very large. So I can guess that everyone now is thinking, okay, but did you now find this metallic hydrogen or not? So let's put the experiment and theory together. In the experiment, we see the reflection rise, in the theory as well, that's good. We see transmission drop, which is also in the theory as well, so that's also good, but this is not enough. So what we did is we combined both, so we combined the data with the model and tried to recalculate the properties of this new material they found. And one of those properties is the Drude relaxation rate, which is directly connected to the conductivity, which we know is an important thing for metals. And we found this value for this material, and we found that they, in current experiments, only generate about 2 nanometers thin layer of this metallic hydrogen, which is, this for now, not enough, but okay. Now, this value, you should compare this to the Mott-E of Regel rule, because this Mott-E of Regel rule puts a minimum value for this relaxation rate in order for something to be called a metal. And as you can see, we're well above this minimum. So from this, we very carefully say, yes, we believe that we have found this elusive metallic hydrogen finally after 80 years. And with that, I would like to thank you for your attention and mention that this work is published in 2 articles.